Yay. Here we go. And I need to press this and keep going on this. Okay, so we're back here with classical algorithms, the second lecture. Last time I was asked to just keep going. So in theory, that's the third lecture, but there's still some parts about going back into this, and hopefully that will work. Does it work? Come on, you. That's the one thing I didn't try. Let me see. Now we go. Now we're talking. Yes. Here we go. So on a not completely serious side, sometimes you get a feeling for what is known and what is not known, for what shows up in specific cartoons, what kind of things have made it into a scientific folklore. Many of you know some of these series, so this is one that I particularly like, which sometimes is a little strange, but often kind of on the point, comes up every day. That's SMBC. And so a little while ago, there was something about how math works. So here's somebody who has an insight and says, oh, this is unbelievable. This is really strange and counterintuitive. I wonder if this is really true. And then not everybody goes with this. Impossible, insane, not just incorrect, this entirely new category of stupid. And then there's debate. It looks right, but it can't be right. Perhaps we could restructure all of math in a way that makes it wrong. And then here's a not so friendly letter, additional decades of debate. You say complicated formula. I see a mother's of horror with loathing the faculty of Cambridge. Changing of the guard, will never understand it. I will never believe it. As I go into death with my final breath, I spit on your theorem. And then a little while later, how do you not get this concept? We spent an hour on it yesterday. And I think for all of you in quantum physics, you can relate to this. And it's actually also in algorithms, because I still remember some quotes by my academic grandfather who came up with a concept of polynomial time algorithms when he was talking about the traveling salesman problem, which we'll get to in a minute again, where he said, I still haven't accepted really that there's no hope for a good algorithms for it, and so on and so on. With that said, let me switch over to another, and I should say here, of course, when you're confronted, whether it is in quantum physics or quantum computation or in classical algorithms, with some concepts which seem a little steep at first sight, you say, oh, that's a difficult question. It is because it is. So sometimes there's generations or at least decades of work that went until we get to how you do it, how it works. So when we don't necessarily take you by the hand and say, now you put in an X and you turn this X into a Y and bang, and there you have it within 1 minute, but sometimes it may take an hour or a week or a couple of lectures. That is because it's still a very serious shortcut, some of the things that you see. So this status of not knowing that you've been experiencing since the last lecture is by design. And if you think that's hard, that's by design. But we will not let you dangle there, but it is also what research is, because we will run into things where together we will experience this again. And we say, like, how does this work? We have no idea. And just saying, like, here's how you do it step by step in an hour yesterday. Come on, how don't you get it? That's not the natural order of things. So let's keep going to another cartoon, which is, of course, maybe a bit more known web cartoon of romance, sarcasm, math, and language. And so here is something which you have, all of you have seen before and seen last time again, was embedding NP complete problems. And here's my hobby, embedding NP complete problems into real life everyday situations. And this is in restaurant orders. So here's the input. That's a menu card. Okay, you see there's a bunch of things that have a certain price. And this is the situation. So here are the people at the table talking to the waiter. we'd like exactly $15.05 worth of appetizers, please. And he says, exactly, exactly, not just up to, but exactly. So you know this problem, we've been there last time, and we'll revisit it again. Here, these papers on the knapsack problem might help you out. Listen, I have 6 other tables to get to as quickly as possible, of course, and want something on the traveling salesman problem. So it's all there, the knapsack problem, traveling salesman problem, everyday life, and of course, NP completeness. With that said, let's go back on tour and let's get back to this challenge. And let me quickly say what this was about. And I will give you some partial answers to this, because some people out there promise that soon everybody will be able to solve these kind of problems with the magic of quantum computers, which is a vast exaggeration, to say the least. But to understand why this is difficult and what this feels like and what a computer has to overcome when you tell it to just do something, that is where we should dwell and linger on this. So that's our input geographically. That is a linear size number of locations. That is also derived input, but because that's a quadratic size distance matrix, you can turn a geometric set of points, or geographic in this case, so it's on a sphere, into a set of pairwise distances. That matrix is not fully filled in because it's symmetric, geometric, so that you just, and you see the diagonal is also skipped. Okay, so it's sort of minimized input. Typical input for optimization problems of various kinds, you have a weighted graph. Vertices, edges in between, edges have a distance, have a cost. And then you have two problems that you should solve. One is find a network of pairwise connections, which means that I want you to draw, and we will do this together in a minute on the next slide. I want you to draw a set of connections such that you can get from any location, like from Chicago to Denver, using these existing connections. Not necessarily just one hop, one step. You may do multiple stops. I mean, you can think of it as a train network, as a road network, as an airline network. You may have to switch and go from one to the other, minimizing the total sum of all these connections. So finding a solution, any solution, is you just say like, okay, well, I connect this and I connect this and I connect this until everything is somehow connected, is pretty straightforward. And I'm standing deliberately in front of this distance matrix because you just draw a few. If you're really not in the mood to think much, you could just say like, I just use them all. Then you'd have to add all these distances, but that could be a solution. Now, of course, the question is how many of these edges should you be using? Those are the kind of things we'll look at on the next slide. The second question, that is the somewhat complementary question to that, which is argue a lower bound. And let me be relatively general here. We're dealing with an optimization problem. And whenever you are dealing with an optimization problem, you need two things, regardless of how you get there. But in the end, you have to have two things. You want a solution that satisfies the conditions for your problem. And then you need an argument that you cannot do any better, or maybe not much better. So there are two things. One is saying there is something which is a good solution. And the other thing is basically saying there is nothing much better. So you're dealing with existence, here's a solution, and you're dealing with non-existence. You cannot do much better. And ideally, if you give an optimal solution, you have to argue that you cannot do better at all. And you can see from this existence and non-existence, that these are two different types of questions and two different types of answers that you need to answer these. We'll get to this, and we'll get to this not just for these kind of problems and number two and so on, but also for these other problems. And I'm looking at this very generally because whatever we're going to do in this project and whatever we're going to do in quantum computing and whatever we will achieve in order to satisfy some of these claims and aspirations and hopes of solving these difficult, important problems, we will always have to deal with these two things. We'll have to find good solutions, and we'll have to find some kind of arguments, either by doing a lot of computation or coming up with smart mathematical arguments, by proving theorems or something like that, that we cannot do better or not much better. Now, this is one problem. Here's a second. The second problem says, okay, instead of just connecting them somehow, we want to find the shortest round trip. Yes, the traveling salesman problem. So there's another level of difference. This is find a good solution, argue that there's nothing better. You will see, you will experience, you will learn that there's another difference between how difficult these problems in both of their aspects really are. And understanding and appreciating this difference between this and that, and not just in theory saying like this is NP complete, this one is not, but also what that means and how that feels. That's part of why you're given not just general thing, and here's a paper, a couple of papers, so you can weight these tables properly, but specific numbers, because dealing with this, understanding where you get stuck, that is important, because that is where research gets stuck, where programs get stuck, where things will take forever. So let's go specifically into this. And now let's look at that and think about this a little bit, about what we need to do here. And if you feel brave enough, if you want to talk and if you want to say something here, feel free to speak up, make suggestions. And I see that Timo is showing him his face, so maybe he's going to say something here.
Oh, okay. Oh, hi. Well, I was just considering, maybe I got the first, as you spoke now, maybe I got the first question a bit wrong, but I thought that we should visit each city just once and just make a way through all of this. And well, I did some, I tested some things, and my best answer was 255 times 10 miles.
255, yeah. So the times 10 is sort of always there. Yeah. We can agree to skip that. So you have a solution of value 255?
Yeah, exactly. So I was thinking like, okay, best ways to start at Dallas. And then the first thing I was thinking, okay, I have to see which cities is best to visit just once. So look at, so for example, I stopped in Denver because going to Denver and back to another city is a very long way. So I just got this way once. And yeah, I got 255 for the first one, just like trying to get always the shortest connection from one city to the other.
So you can do that. Do you have this like on a piece of paper? You can hold this to the camera? Okay, well, I mean, in principle, we could all now look at this and check this, right?
Yeah.
Let me go a little closer here so I see this. Okay, so it's bifurcates here and so on. So now here's the thing. What we need to do, what we would need to do to check Timo's solution here is two things. First of all, we'd have to check whether this is feasible, whether it satisfies that condition, which is stated here, that connects all cities, has minimum total length. Well, the first part, feasibility, is what we care about. Does it satisfy that condition that it connects everything? And it looked to me in that picture, it was a bit hard to see in that resolution, that that was okay. And you could convince us by saying like here, 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 here. In principle, if this was a really complicated network, what you could do is look at all pairs of cities and give as a certificate of feasibility a path from one to the other and say like, here, check, this works, right?
Okay. Yeah, I could.
You could do that.
I could draw my way on this. Yeah.
Yeah.
Very simple.
I'm not asking you to do it. I'm just saying,
okay.
In principle, and this is something, if you have a solution, it's not hard for us to double check that, right?
Yeah.
The second thing is 255. 255. That's a pretty good answer. We could now look around and ask, like, does anybody have something better?
I think I got 231, I believe.
231.
Yeah,
Yeah,
I
I
also got 231.
Okay. So we're doing a Dutch auction here. Anybody lower, right? So like, can you do better than this? And whenever somebody has a better answer, we can just simply check that. And then Timo would say like, okay, well, you know, I thought about this. Maybe you made some assumptions that were not necessary, which is perfectly fine. Andrea, can you hold this up? Do you have this on paper? That does look pretty good. That indeed does look pretty good. You said 231?
Yes. 231.
Okay. As I also have something else to show here in a moment. So let me just do that and go along the way. So what I did here is I said, okay, well, you know, I have to connect Denver somehow. It has to be connected to something. Otherwise, where can I go? And I cannot get to Denver. So I took the shortest edge from Denver anywhere. You can convince yourself, how would you do that here? You look at Denver, you look at that row and that column, anything related to Denver, number 3. And you see the nearest neighbor is number 7. That's Omaha, Wichita. Wichita, did I use Wichita? Indeed, Wichita is closer, 51 is less than 54. Anyway, that's the nearest neighbor to Wichita, so that's easily checked. And that costs me 51. Now, while we go along, at this point, I can say, this also has a partial answer to this. Because, which we didn't address, so have you thought about, have you, Timo and Adea and others, have you thought about this lower bound as well? It's the harder part, so it's perfectly okay if you didn't.
Yes, but only a very trivial one. So it's very not sharp enough to be useful.
So what is it? What's something you can come up with?
Well, so I thought that if you have n vertices, I need at least n-1 edges to connect them. So I sum the n-1 smallest edges. But it's clear that that's going to be they're going to be bad, so multiple connections in that case.
What number did you come up with for that?
Blah, 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 blah. I got, what did I get?
I mean, that sounds pretty good. So
I think 195, I think it was.
195?
195, yes.
So when you look at this, you check like what's the shortest edge here. I mean, there's a 17 that will show up here somewhere, but it was, I think there was.
Yeah, I don't remember exactly.
There's a 16. I think 16 was the shortest edge, right?
Yeah, yeah.
So just roughly 9 times 16. I mean, this is worse, even worse than what you said.
Well, yeah.
9 times 16 is 144. So there's a simple argument that says, hey, come on, you cannot beat 144. Because here's and this would be a mathematical lemma where you say, in order to connect 10 cities in some way where everybody can reach everybody, possibly indirectly, you need at least 9 edges. Because in the beginning, nothing is connected. And with every edge you throw in, you may connect something that was formerly not connected to something else to what is already your hub, your traffic network. So if you say, for instance, I start in Denver, everything needs to be connected to Denver, then I draw an edge and I get a new connection, and I draw another edge and I get a new connection, and I draw another edge, I get a new connection. When you think about this carefully, which we're not doing here, this is pretty sloppy. I mean, intuitively, it makes sense, but mathematically, that's where you would argue that, yes, I need at least 9 edges. For us, it's fine to say, like, yeah, I mean, that sort of seems clear. And I will do this in a moment. So I will draw 9 edges. And you can do this. Now, this is the part where things get a little tricky. So you have a good solution, and we'll look at what I came up with in a moment. You have a good solution. You maybe you find something better. And you say, like, oh, no, I did something differently here. Arguing that there's nothing better, that is always the hard part, even for a problem, which this actually turns out to be. It's a couple of longer lectures in an introduction course to optimization, which is a lot more than what we want to do here. I want you to sort of get a feeling for these things and see, like, yeah, here's a couple of lectures that we could do to introduce trees and minimum spanning trees and algorithms for this and so on. But that is always the harder part. Even when there is a good algorithm, a good solution, that's where you do the work. Finding a solution is one thing. Arguing that it's the best, systematically finding good solutions, possibly enumerating, doing some shortcuts and so on. I'll be talking about that a lot. And even if we use quantum computers, we'll be talking about that a lot as well. But arguing why you cannot do any better, that is really the difficult part. Even when you can do it, it's which requires thoughts and ideas and arguments and theorems. And very often you cannot even come up with that. So let me just continue here a little bit and just being plausible. So now I have this partial network of Denver and Wichita. Okay, these are connected, and it's the cheapest way for Denver to connect to any place else. So even without Abo's nice argument that you need 9 edges, it is a lower bound that I have, right? 51. You cannot do better than 51 because you need to connect Denver to something, and that's the best way to do it. Okay, now let's see. Now I have this partial network of Denver and Wichita, and I need to connect this subset. I need to connect it to the complement, to these other. There needs to be an edge which connects this subset to that subset of 8 other edges. So let me use the cheapest way of doing it in any way. And that means I check that. And it turns out the cheapest way is to go from Wichita to Oklahoma City. That's the 16 we have here. That's the 16. And now I have this subset of 3 connecting this subset of 3 to something in the subset of 7. What's the cheapest way of doing that? Now you see there's a bit of structure. I'm doing something systematically. You can turn that into an algorithm, and you can do even more. You can argue that this algorithm does something locally optimal, so that connecting this to the complement is something I cannot avoid by doing this to another complement. So there's some math involved here. There's some structure of nested sets and some structures. Like I said, there's some theorems and lemmas you could prove here, and you can look these up easily about minimum spanning trees and such. Okay, so the next cheapest to connect that to the complement is this. That's a 20, and you can do this, and that's a 17. And when you have these 5 and you want to connect it to something in the other 5, the best, cheapest way is to do that. That's just another 20. And here's another 21. Each of these steps now where I'm drawing an edge is a place where I check this and I check here what is the best way of connecting. Here's another 21. And up here, there's a 29. And now I'm getting to where I want to connect this one, the cheapest possible way to all these which are already connected. And I'm getting checking this, I mean, final step, Minneapolis. What's the best way to connect Minneapolis? You see, no, Minneapolis here. So that's the best way to Omaha. And that's a 36. And if you add these things up, you do indeed get a 231. Now, at this point, and we heard this from Andrea and from Bo, yes, 231. And at this point, Timo can check and say, oh, yeah, 231 is better than 255, because maybe, there's nothing wrong with this, because maybe you were trying for something else, you were not allowing some branching here, you were just going around once, which gives you a feasible solution. So it is much better to get some feasible solution, even if it is 255 and 231 is possible, rather than saying like, I still haven't found the optimal solution, so I'm not giving any solution.
Yeah, you're right. I think I just got the difference between 1 and 2 not correct. I thought I have to be in each city exactly one, or like making a round trip just without getting back to starting point. Yeah.
There's nothing wrong with that. So you could argue, I mean, we could argue depending on mentality, whether I stated this nicely, or whether maybe in real life there are some assumptions which you make where it is nicer and better to make one round trip because you save a few things and branching points and so on and so on. Absolutely no problem with that. And even if you, which you are not, but even if you are just lazy or somebody just runs something quickly and says, here's a solution with 255, that's what I can come up with. It is better to have any kind of solution than think forever and not have a solution. I mean, this is the same thing when you have an exam. It's better to give some relatively good answer and to give some credit than to think forever and not dare and then just get 0 for this. Anyway, so we have a solution of 231, and you can visually look at it and convince yourselves that 231, is what you need. I mean, you see that everything is connected to everything. And you can also check by adding these numbers, 29 plus this is 50, and there's a 56. So we got 106, 123, 143, 194, and then you get another 37, 194 and 37, that's 231. So that's elementary adding. So this picture alone, regardless of how we got there, gives you an answer for a solution that is feasible and that has a certain objective value. So, this can be achieved. What the harder challenge is, and there are different ways of doing it, is convincing yourselves and others, and doing that systematically by means of an algorithm or mathematical theorem, because the algorithm that we used here always does something nice, and you can be sure that this is really optimal. The answer is, it is optimal by means of how we went about constructing the solution. So there's something implicit in this algorithm. So there's an extra theorem that says, if you do the computation this way, you will get an optimal solution. So the certificate of optimality that you have here, that certificate, that is part of the algorithm, and that is part of proving a theorem, using some structure, using some auxiliary properties and so on, that it will find the optimal solution. Now, it goes along the ways of arguing that you always take the best locally. And that works here for this structure. It can be tempting to say, I'm always doing the best locally, and that will give me the best solution. It is not always true. You can be mistaken here. And what I'm not doing here today, and I'm deliberately leaving this out to give you another chance at the more interesting and more challenging and more difficult problem, this one here. So what you can do, and Timo showed us a possible way of doing it. I mean, if Timo was holding up that solution again, which was a trip from Dallas to Denver via all these other locations, and you would close it by adding another edge, which we could now do. I mean, 255, and then we go from Dallas to Denver, here Dallas to Denver, that's 78. So that means 255 plus 78, that's 333, correct? So what Timo has with this, what he's holding up there, and what you can and should think about is a feasible solution of length 333. That is a pretty good solution, I can tell you that much. What I want you all, if you haven't done it yet, because you think, I don't know how to approach this, which is fine, think about this again. Think about how you can you find a better solution? And that is the really important one. Can you argue a lower bound? Now, I can give you a conditional lower bound. A conditional lower bound is saying, like, suppose we know and we can prove that this is the best possible solution for this, where I've only waved my hands over. So I have not really strictly given you full proof of this. I haven't given you a proof of this lower bound. But if that was true, I could say, like, well, you cannot do better than 231 because a shortest tour here will connect everything. And if that is the best way of doing it, you cannot beat the 231. There are other ways. So Bo was giving us a really good idea here. But we're saying, like, look at length of edges. So we know that a tour has to have 10 edges, 10, right? That's clear, 10. You enter and leave each one once. So you need 10 edges. So we could use Bo's suggestion and say, okay, take the 10 shortest edges. You can just simply use the 10 shortest edges and get that number. So you said with the 9 shortest, you had, what did you have, Bo?
What was it? 195, and then with the 9, and then with the other one, it would be
So I mean, you look at this and you look at
maybe, yeah, 224 maybe. Was that yeah, what?
224.
Yeah.
Okay.
I think so. Yeah.
That is something. Of course, you could start looking at this more carefully and say, like, oh, come on, I need to use an edge from Denver. And then you can start playing with your edge set there and say, like, okay, I mean, I've used all these things which are locally here, but one needs to be Denver. Come on, I cannot avoid Denver. And you could also say, but I need 2 edges for Denver. So I'm actually using 2 edges for Denver, the 2 shortest edges for Denver, and 8 others which are here. You see how this goes, right? So you can play with this bound. You can argue that something is better. You may get relatively close. So we take Timo's solution for the tour of 333, which, like I said, is quite good. And we can try to close that gap. So some people, and when I first showed this to the PIs of these projects, started doing something relatively what full professors sometimes do, use brute force. So David Gross was using just enumeration. He just enumerated all solutions, 10 factorial, that's a 6-digit number, that's not so bad, 10 factorial, and says, okay, that's the best one. It turns out there's more than one best one. There's 2 optimal solutions, but that's just luck. So that's a brute force solution. You look at all the solutions, but that does not necessarily work on scale. It doesn't scale. Looking at 10 factorial possible solutions when you have 10 cities is just doable. When I give you 20, it gets already harder. When I give you 100, forget it. When I give you 13,509 post offices in the US, that's much worse than the end of the universe and all these sorts of things. And that's the kind of space where we're looking at, and that's the kind of claims that are being made out there about quantum computing, that quantum computing will be able to do this, and possibly faster than classical computing. So that is why we are spending time and revisiting this. And what I want you to, if you haven't done so, close that gap. Like, how close can you get it? And what kind of arguments can you be using? Even if you will not, and chances are you will not close this gap to 100%. That is exactly what is going to happen with some of these difficult problems. And this is exactly where our challenges will be to, like, can we close this gap? What can we do? What happens? And what kind of arguments are we using? Are we using enumeration? Are we using good luck and guessing? So Timo had, like I said, a good idea here and gets a good solution. Some ways, maybe it's luck. Maybe it's something systematic that we're using. And where can we use some other structure to doing this? I will get back to this. I will show you an optimal solution to this, and I will give you an argument to the second question, but that needs a bit more work and a bit more preparation. Let's keep going a little more. Get on to the next set of questions that we had, which was past. There's a question, please.
Sorry, yeah, can I interject before we move on to the second
Absolutely.
problem? So yeah, I should say, yeah, we did get our hands dirty with just starting to enumerate all the possible solutions of this problem, but we got a lower bound. I'm not sure if this is the right time to discuss about like analytic lower bound for the second problem. Also, I tried it for the first problem. Should I explain it now, or we might?
Here's what I would propose. We can leave this for the after session, after I'm done with this. So people who want to hang around and talk to you can do this. For those who don't want to, like, because you had a bit of a head start, yes. Right? Who say like, oh yeah, I want to hear what Wahide has to say here. They can just join you like after the session. Okay. And those who don't want to hear any spoilers can sort of say like, yeah, no, next time. Okay, but thanks. Okay, I'll keep going. Let me just be a bit quick here. Bang, bang. So greedy is good. Now remember these other things. There were some remaining problems was referring to exam problems. So that was problem numbers and so on. This was the question passing the exam. There were 16 remaining exam questions, and these exam questions came with cost and benefit. So you spent minutes and you would get credit points. And the question was, can he pass that exam? He had 120 minutes left and he needed 44 more points. So the question is, can you pick a subset of these such that the total sum of these second entries in these vectors, the minutes, does not exceed 120. And the benefits, the third entries in each of these 3 entry vectors is at least 44. And then there was another variant of this. What happens when partial credit is possible? I don't know if you thought about this, and Timo is nodding. So, I mean, since Timo is the brave one, anybody should feel free to just speak up and talk. Dominic, maybe if you want to go, I've stretched well and rested, I hope. If you want to go, Timo, let's give Dominic a chance if he wants to.
Okay, I'm sorry for stealing your show, Timo. I just thought we solved the task too, so I started my camera. Yeah, so the solution is that he can pass the exam. Because you can find a solution where the number of points are enough, and that solution, I mean, of course, the solution is not optimal, but it doesn't have to be optimal. It just has to pass. To be true, I don't remember the exact solution. I just know that we found one. And
Okay,
the thing
cool.
is, to the other answer, what happens when partial credit is possible, then it's possible to find an optimal solution relatively easy, because you can it's not NP complete anymore, the problem, because you can just give every task a score by dividing the minutes with the number of points it gives, and then you know how good a task is, and then you can just go up and take good tasks until you can't take a full good task anymore, and just fill up the rest with a portion of a good task.
That is very well said, and it's absolutely correct. Before I comment a bit more on this, let's give Timo a chance to add to this if he wants to, and anybody else, of course, should feel free to speak up as well.
No, exactly the way that I worked that out.
Okay.
Just in the end, it all fell together because we could take this number 16 to get to 44 points. Okay.
So let me, and not coincidentally, I have something prepared here. We didn't agree on this before, but it's also because Dominic was talking exactly about these ideas. So one thing is, you look at these and you look at their relative cost or their relative value, if you want. So these are sorted by either you can say like minutes per point or points per minute. In one case, you want to have few minutes that you need to gain a point. In the other, you want to have many points that you get per minute. So depending on what you prefer, how you look at it, it's the same kind of order. So you see here, this first question, you can get 4 points in 4 minutes. If you could maintain that pace, you would have 120 points after 120 minutes. That would be wonderful. At the other end of the scale, here is a question which takes you 32 minutes for get a measly 2 points. And that's really not so good, because in 120 minutes, you'd have less than 8 points, and that's definitely not enough. And this is all sorted. And you see 8/5, that's worse than 4/4, but actually the same as 16/10 and 20/9. So you do this and you say that ratio, and you see this is a ratio of 4, that's a ratio of 4. So these are equally good. Okay, so you could play with the order here, but we'll get back to this in a moment. And it gets worse and worse and worse. So what Dominic was saying, the natural approach, the natural try is here to just go along here and take them in that order while you can. And let's just do that. So here I keep track of the total cost it has and the total benefit we have. So you see there's an X. This X is a variable. And in fact, here it's a 0-1 variable where we say we pick this or we don't. 0-1 variables, of course, bits, they come into play in computer science in general. They also come into play in quantum computing because you switch from 0-1 to maybe something else, qubits, which are an extension and all that. So we keep track of this. So we set this variable to 1 when we pick an item. And let's do that. So that one we pick, this gives us a total cost of 4 and a total benefit of 4 as well. And if we take the next one, then you see this goes up to 12 and this goes up to 9. And we just keep going here. So that goes to 28, that goes to 19. Here we got another 20 and another 9. So that's 48 and 28. And we keep going. We keep track of how much we spend and how much we get. Now that's a relatively expensive one, 40 minutes for 10 points. That's 96 and 40. Come on, 96 and 40 here. And now we have to be careful because this would take us over the time. So we're not going to take that one because we cannot afford that time. And the same thing here, we shouldn't do that. But hey, look at that. That's a 24. And miraculously, that just works out, 24. And with these 4, we get 44. And at this point, what Dominic says, yes, he can pass the exam. Wonderful and great. And it doesn't even matter whether we use something systematic or whether we just did a blind guess or something in between, I would say, but we just did here was something in between. We came up with a good order and then we just did this and we have no idea whether this is really the best solution, but it's a solution that does the trick. Is there an argument that we cannot do much better? Here we could do it with the brute force enumeration again. How many possible subsets do you have? I mean, you have 16 of these possible choices. For each one, you have a 0, 1 variable. So you get 2 to the 16. 2 to the 16, that's 65,536 possible subsets. You look at these and say, which one satisfies this and gives you the largest? So you could do that by enumeration. But again, that's not scalable. That will blow up exponentially, and I'll show you a few pictures in a moment. Now, let's, so here you can pass that exam, wonderful. And sometimes you just make a guess or you just try something smart and you get there and you say, here, come on, what do you want? This is a 44 and it's fine and it works. Now let's look at, that's sorted by this, somehow out of order. Look at this. So that's the knapsack problem, but here's a twist to that knapsack problem. So we have these objects, that's our inputs. We have that size bound, and we want 0, 0, 1 variables. Actually, no, when you look closely, you see there's no longer 0 and 1, the set, it's 0, 1, the interval. So for each object, we pick a variable between 0 and 1, which gives us the fraction of that question that we're going to do, and a fraction of the time we're going to spend on that, fraction of the points that we get benefit for that. So now you have the same kind of description here between 0 and 1. Okay, fine, fine, fine. The upper bound, and you want to maximize that. The only difference is that you used a larger set of solutions, a larger set of choices for your variables. And when you do that, this thing here, that's partial credit. And it's also called a relaxation. We relaxed the constraints, we relaxed the conditions, we expanded the feasible set. And it turns out that makes things easier. And that's exactly what Dominic was telling us a moment ago. So let's revisit this again. We sort this by that again. We did this. We keep track of this. We keep track of that. And we just keep going along here. We use that. Okay, we get these numbers again, and we use that. We get the better numbers, larger numbers. Keep going, keep going, keep going. Okay, and here was when with the integers, when we only could use binary variables, we could not use that because it was too big. But now what we can do is we take a part of this. Dominic, did you try out these numbers here, or?
We started and then we tried it out for the integral problem, where we only can use full numbers, and for the fractional problem, we just realized that that you can find an optimal solution pretty easy. Didn't calculate it any further.
Okay, well, but this is exactly doing what you suggested. So this is where you would have gone if you had continued this. There's so many things to do. So how much of this should you be using of this item here? What fraction? What should the x variable be for this item?
Well, the exact fraction of time that is left.
Okay, let's do that math. So let's do that. and we want, how much of this can we afford? So how much is left? Well, we have 120 as the capacity that we can afford, time, and we have used up 96. So what's left? That's 24, right? 120 minus 96. 24 is what we can afford. So we want 24 out of 40. What is 24 out of 40? That is 0.6. If we use that, we use 0.6 of that. This is 6 of the 10, which gives us that and gives us that, okay? This. All right. Think about these numbers, and it's if you do this. Now, what this does, it gives us a better solution for a more generous problem, for a larger solution space. And I'm going to do two things now. I'm going to argue that for this relaxed problem, for this fractional problem, this is indeed the best possible solution. So the first thing is we get a feasible solution. And the second thing is we actually get an optimal solution for this problem where we are using fractional x's or we're using partial credit for these answers, okay? So again, the same thing. For this one here, I just need to argue that, yeah, this satisfies the conditions and hey, there's a 46 you can get. This one needs an argument. And for that, I will give you a proof sketch for why this algorithm here actually does give you a best possible solution. And the first thing, feasibility. So what we did here, I didn't run you through that. That's the pseudocode for the algorithm that we used. So, I mean, you sorted these things and then we said, while you can afford to take the next thing, you just did it. You just set it to 1, you took it in whole. And then at some point after you're done here, you're using the rest of the capacity to determine the fraction, which was the 120 minus 96 divided by the 40, which got you the 0.6 in this example. Pseudocodes looks always impressive, even if when it's short, but that. So this is exactly what we did here. We used all these, and then we took a fraction of these, the fraction of 0.6, which was precisely that 120 minus 96, so it was at 24, and we got that. Okay, so that is by construction is feasible. It gives you precisely that value. Now let's convince ourselves, and I'm not giving you a written proof, I'm giving you a visual proof, which you could turn with a bit more homework if you wanted to into a formally stated mathematical proof that you can write down in a textbook or something like that. So here is the set of items, and these items are sorted according to the relative values, so points per minute. And this is denser and this is less dense. And then we're looking at the variables here. So what we did is, according to the sequence, we put them to 1, to 1, to 1, to 1. And at some point, we only took a fraction. That is the solution we constructed. So there's one particular index where we only take a fraction of it. So now let's assume there was a better solution that did something else, maybe something magic, maybe some tea leaves or something that looked different. And let's assume that this solution we constructed was worse than another one that was worse than an optimal solution. So that would have, on the x variables, would have to have a different structure. So now an important thing is all these here, the first ones here, all of the benefit we're getting is larger than 0 because we're not going to attack, we're not going to pick something which gives us a negative or a 0 value. We can just ignore those. So that's without loss of generality. I mean, why would you do something which gives you a deduction or no benefit at all? Okay, so now when you look at this and you look at the these, there needs to be an index where this better solution has a higher X value than our greedy solution. Otherwise, you're not going to be better, because all the benefits are positive. So if these are all positive, you need to have some X, K, which has a larger value. So that is the claim. There needs to be some K for which our solution value, the variable is less than that here. And now all of those are the maximum possible value that they can be. They're all ones, right? This is what we did. They're all ones. So none of those can be larger than 1, because the variables are between 0 and 1. You take it or you don't, or something in between. So that must be something bigger here, which means that it's got to be one of those here. One of those. That. And okay, so we have reduced that. It's not one of these. And that also means if we can afford to spend more time on one of these problems back here, that we must have not spent time up here. Because we're fully, I mean, the sum of this, the sum of the xi, zi is equal to our bound. So we must be able to afford this, which means that there must be one of these in this part here, in the first part, where this green is bigger than the red. Because see here, I mean, we were able to afford some time here, so we must have spent something. You can write this down in terms of the X's and the Z's and so on, and then it follows directly. Now, but what does that mean? So here's something which is not fully exploiting the time we have, and that is spent on this. That means there is an L, that's the L, where this variable, the green one, our greedy one, that we came up with, is larger than what claims to be an optimal solution. Okay, fine, these we don't care about, maybe they're at 1 as well. But now here's that thing. This is bigger than that. So now what we can do is we can reduce this. We make this a little bigger and we make this a little larger, because we spend some more time that we spent on this problem, on that question. And so let's just do that. This one here and that one here. And with that, we deduce a bit of time here and we add it to here. That's the variables, right? Or the time that you will end up spending. And now when we look at the benefit of spending this time, you see that you get more out of that time spent up here than up here, because they are sorted in this way. Which means that you're definitely not getting worse by doing that. You may be getting better. And if you continue this argument, then you see like, well, that's not optimal. Or if you are really careful about ties between these values, then you can argue that this is at least as good as that, which is a contradiction to that. Waving my hands here over this, I think you get the idea. And one important part is that writing this down in this way, in this mathematical way, is what's done in the textbooks. And that's how you write these things down and you argue line by line. I mean, you see here that implies that implies that applies somehow. But when we think about this algorithmically, I do this visually. I mean, I think about in my head, or I write this down, or so on and so on. Going from here to here, that's another kind of coding that works. Now, what the consequence is, this has a few consequences. So you can write this down more carefully. What I'm arguing here is that this greedy algorithm for the fractional knapsack, partial credit, gives you an optimal solution. What that also means, and let me just go back here. What this also means is a couple of things. So that 46 is best possible. But it also means that for the integral problem, you cannot do better than 46. Why is that? The optimum for being allowed to, if you want to use fractional solutions, cannot be worse than if you are not. I mean, you can not do it, and then you just say, okay, I don't like fractionals. I just take integers. But the integer solutions are part of that set. So a 44, and okay, but you have this 46. So that also means this thing together with that theorem here gives you an argument of a bound. So we solve this relaxed problem and we get a bound. This is something we will revisit. So this is an argument that comes up and so on and so on. And it's something that people do all the time when they know what they're doing. Okay, let's do one more thing. And let's go to this subset sum. So I see Andrea is showing her face. Maybe you want, no.
Yes, actually, so I also got 46, but I did a partition a bit differently. So I had 5 full ones, and only for one set I took, I split it. So I took only a percentage. But so I see that you have 6 full times with a minute and 1 partition, but I have 5 and 1 partitioned. And my question is then, why is your solution better? Why is it optimal?
It is, well, optimal.
Or
I'm not saying my solution is better than yours. If you got 46 and I got 46 and both of our solutions are feasible, then they're equally good, right? So 46. Now we could look into secondary objectives, like how many of these questions do you select? And I can tell you, I can show you all why there was a difference. When you look at this, what you see here, there are ties, right? So here are ties. This is an 8/2, that's a 4/10, that's a 4/10. So these are equally good. And now here I use something relatively small, short, and I used it in my solution. So what I suspect you did is just say, I ignore this. And then instead of having the 8/2 in here, so you didn't use a 24, I think you used a 32, right?
yes, exactly.
This gives you, because these are all tied, they're all the same value, relative value. So instead of spending 8 minutes here, you spend 8 more minutes here, and then you get the same solution.
So we consider them equivalent in the end.
Yes.
Because I was also thinking in minimizing the number of problems that someone is solving.
I'm sorry?
Yeah, I was thinking also in minimizing the number of problems that someone is solving. And
you can do that, but I didn't ask you to do this. So for this problem, these are equally good solutions, equally good. So I think I answered your question.
yes, thank you.
Good, thanks for the question. So thinking about these things and where this comes from, you can see that if you understand the structure of these, you can, with this information, you can say like, okay, this is probably what you did, right? So, and this is how this happened, because there's some order. Let me just do this one more thing here, and then I need to go to this other presentation I have, but you can of course continue between all of you. So this one more thing I want to do. Arduous arguing. Yeah, okay, all this go. Argue. This is a mathematical argument, but the next argument is if you want a more tedious, because there's just brute force enumeration. Okay, skip, and skip. Here we go. It was this. And that should sound familiar when you remember this XKCD with a menu and the waiter. I want exactly a subset of a certain value. So that one, okay? I want a subset. If these are your appetizers on the menu, I want to order exactly 120 minutes cents size worth of these. Here they are. And here we are again. And you can do that. 7 plus 53 is 60. 31 plus 29 is 60. That together is 120. And you can just quickly check this whole thing again and say like, okay, easy. If I have a solution, I can just check it and say, that's 120, that's 120. Same thing again. Now, this is a decision problem, not an optimization problem. It comes out of an optimization problem if you do the following and you say, actually, what this is a knapsack problem where time equals points. It's an integer knapsack problem where you need to come up as closely as you can to 120. And it's a special case where you want to actually hit it right on the dot. If it was fractional, then you just take it and you cut it and take a part of that. Now what I did was I changed that to from 24 to 20 and this from 57 to 53. And that gives you a certain number. That gives you a certain, here, 53, come on. Yeah. Oh no, it's 57. I went from 53 to 57. So I don't know if you tried this with the new numbers. Did anybody try that? No.
I tried it, but I didn't succeed.
And for a good reason.
Yes, I mean, okay, maybe my reason is not so mathematical, like very rigorous, but I was looking at the last digit and I was trying to see if I can get 0 as the last digit. And it was only one situation when I managed, but that situation would give 110 with 130. And obviously it wouldn't satisfy the previous condition.
Yes. And you're perfectly right, because the reason why you didn't find a solution, and you have a good excuse, because it doesn't look like there is one. And in fact, there is no solution here. So if you all tried this, you would get stuck because there is no solution. You cannot say like, oh yeah, here's the 120, like in the slightly changed numbers. So let's just quickly run through this. And the thing is, let's do this and argue. So I used a slightly different approach than Andrea did. I didn't look at the final digits. I just used, looked at the largest items. So if you have this 57 and these other things and so on, then you can try out total, I mean, the total number. You can put one on the top and one at the bottom. So for each one, you have 2 possible choices. Let's move this and take this and move it up. Without loss of generality, then we have 63. So this one needs to go here. This is confirmed. This is fixed. And then we have here a 63. And now we can try what happens when we move the other thing. So if you move this up, you get, this is still tentative. Maybe we try. It goes up here. If it doesn't, then it goes down. So what do we have left? 63 minus 35, that gives us a 28. Come on, where's the 28? Here's the 28. And now this doesn't work. This doesn't work. This doesn't work. We can try the 20. If we move that up here, then we have 8 left, and that obviously doesn't work with these other numbers. So that doesn't work. That doesn't work, and that only leaves 11, and we have 13 and 7. That doesn't work. So that doesn't work, which means this was an attempt that doesn't work. So let's move this down here. And now we know it has to go here. And that leaves us with a 63. And we try this one, 85 here. We try this one, moving it up. That leaves us a 32. And now that 31 leaves us 1. So that's bad. That leaves us a 3. That's bad. That leaves us a 12. That doesn't work. This leaves us a 15. And that's not enough. So that doesn't work. And that means that this one can't go up here. So That doesn't work, and that doesn't work, so we move it down. Bang, down we go. And now here we have the 63 and we have the 54. Now we tried with this 131, so this one also doesn't work. I mean, no way. So that has to go here, and we know this, and then we have only 23 left, and this one has to go up here because that's not enough. And that 20, so we have this, that 20, if we move it up here, there's a 14 left, but it doesn't work here because there's 23, that's 3, that's not enough. So it has to go here, and now we only have 14. And you see that doesn't work, and that doesn't work, and the whole thing doesn't work, okay? So that was arduous arguing or tedious trying, whatever you prefer. And that is what I did here. This is hopeless. I tried, so without loss of generality here, and tried left and right, up and down. And you see this is an exponential size set of possible combinations. And yeah, for each one I have 2 choices. So that's an exponential size tree enumeration, left, right, 0, 1, yes, no. And there's exponentially many cases. And the question is, can we save effort? And let me just go back here one step. So that's the question, if we can save effort. And this one, convincing yourself, looking at this case enumeration is an important one, because we can do it this way. We can argue there is no solution, but the question is, there's one thing to have an optimization problem where you say, like, here's a solution. Yes, there is one. And here's an argument, whether it's 255, 231, 333, or something like that, which says, yeah, it's good. But if you have no solution, what do you do then? How do you argue that there is no solution? And that's the kind of thing where I'll pick up again next time, and where I would encourage you to look at these things again and remember last time there were already some structures. There was NP hardness proofs. There was an NP hardness proof for subset sum, which says like, oh, it has some implications, which are there for a good reason. And let me say a few final words here for today, because looking at these things more than once, revisiting them, taking some of the theory that you saw into the context, questions, practical solutions, concrete specific numbers, and looking at these things repeatedly is how the human brain gets things. We're not computers where you just download this theorem and then you say, I apply it, I have the software and I use it. It works for a computer, but a computer doesn't understand it. And a computer is not creative enough to say like, oh, I can use it in this context. The computer doesn't have to think about it, doesn't have to understand it, just does it. You upload it once if your software is good, and that's it. But the reason why we have a big advantage over the computers is that when we understand these principles, we can reuse them in a totally different context. And the price is that we need to think about this more than once, because we get the more abstract patterns. And that's why we're spending today on something that you saw last time, and where I would encourage you now to go back and look at these things and talk about this with the others. Maybe you want to talk more about the traveling salesman or life in general or whatever else. With that for today, I will leave it at that. And I would ask Arne to stop the recording